The mathematics of general relativity often seems difficult, abstract, filled with tensors, curvature, and the geometry that feels almost unreachable. But it does not have to be that way. In this three-part video series, I will take you through some of the best books and the best learning methods that make the mathematics of relativity clear and logical. In due course of time, you will see that the flow and method how to actually learn general relativity is actually easy, and it is something which you can learn from its very mathematical foundations. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first video on this series of learning the mathematics of general relativity. Well, before we go ahead and talk about the books and methods, let us first learn at the very basic step the geometry of space-time. Now, every theory or every once in a while a theory does not change how we calculate, but rather it changes how we think. And this exactly happened in Einstein's relativity. Einstein's theory of relativity did exactly change our entire perception and understanding of space-time and gravity. The mathematics of force, which was perceived and discovered by Newton, is actually given by the basic fundamental equations F equals to ma. But as we see that general theory of relativity defines gravity now as a curvature of space-time. We can say that gravity is a kind of a manifestation of the curvature of space-time. So the apple is falling not because of the force, but because there is a central mass, for example the sun, which is heavy, and all the orbits and the planets and the small less heavier particles are actually rotating around this heavy mass, not because of force but because of gravity. The basic concept that we perceive in case of a straight line now are considered to be geodesics. Well, geodesics are actually the straightest possible path, but it is defined in a much elegant way with a kind of a complex mathematics. The Euclidean distance, which was perceived with this kind of equation, is now known as a geodesic equation. And the very famous Newton's law of gravity is now being redefined with Einstein's field equations. So all this actually caused a kind of a big change in terms from the force to the gravity, which is a curvature of space-time. Now, in case of explanation which we used to do with force, we explain force through forces, things that pushes then pulls. And now what we see is that Einstein showed this not as a force but a manifestation of the geometry, which is a curvature of space-time. Reality was made of, so it actually led to what is called the geometric understanding of reality. Reality was made of objects in space and forces that are acting between them. Space and time were just stages, passive backgrounds where things actually happen. Einstein changed that completely. Space and time were now considered to be more dynamic. They are interconnected and they are curved. So matter and energy shape the geometry of space-time. What we once thought of force or space as something different, Einstein shows that space can be united with time, with something which is called a space-time. The most revolutionary thing what came is that geometry stopped being acting as a tool to describe reality, but it actually became reality itself. So the geometry which was perceived just as a tool to describe something in terms of internal and external curvature, this geometry actually became the reality itself. And because there was a complete shift in terms of understanding mathematics, etc., we actually from here take a threefold understanding or threefold aspect to this entire series which we are going to learn. So when we are learning something from the concept of geometry, when we are moving from force to the curvature of space-time, we are taking a threefold approach. First, what we are going to understand here is that the conceptual mathematical foundation. Here actually what do I mean by in the first part we will learn why the notions of force breaks and how actually this notion of force is being replaced by what we call is the geometry. The second part is where we will learn about the formal mathematical exposition. That means how the derivations, the Einstein field equation, relationship between matter and space-time, energy and space-time, all this we are going to learn in the second video, that is the mathematical exposition. And third, as we know that general theory of relativity is a theory of geometry of space-time, we are going to learn the evolution of geometry. That means from Euclidean to non-Euclidean, how it was elegantly weaved in the Riemannian geometry and further ideas on the geometric evolution. Now, as you can see, all these three are related. If you don't first understand the concept and the mathematical foundation, then you won't be able to know the mathematical exposition, the derivation, and thereby you won't be able to know the geometric evolution of ideas. So as these three things are related, so from here what we come are three basic questions. The question is that how does geometry stop being an abstract mathematical idea and how it became the structure of reality? So here we are going to actually learn about manifolds. For example, tensors are the universal coordinates which describe physical quantities, and it shows the curvature replaces the Newton's notion of force. The second question is that once geometry is physics, then what does the full mathematical structure look like? That means how we define tensor analysis and differential manifold, how the field equations actually expands in different coordinates, Schwarzschild metric, and so on. And finally, on the third front, we ask this question: how did the language of geometry evolve until it fully described the physical universe? Here we will start with Euclidean geometry, which is flat, rigid, a kind of a human scale intuition. Then we will move into non-Euclidean geometry and finally into Riemannian geometry, where curvature changes from point to point, the mathematical seed of general relativity. So these are the three basic questions, these are the three basic notions of our entire journey in understanding the strong mathematical foundations of general relativity. Now the book that I would be talking about, not only this book but for several other books, and the approach that I would be taking is basically the physical and mathematical foundations of relativity, written by Romano and Fernari. Now this is basically the cover of the book. Not much I could find out about the authors, their life, and about their links, all those, but what I can found is that I got two links from ResearchGate, and this is about their authors, their citations, publications, and all. Now one thing I would like to mention and make a note before I go ahead into this video is that this is a heavily mathematical book. So I expect that the viewers are taking it in the right spirit. There is less amount of intuition and analogies which are given, and more of the actual mathematics that is required in order to understand. Now this is the right time that I would go ahead and explain to you the table of contents, but I would not do in the general way that I used to do in other videos. First of all, I will tell you the first basic step in understanding general relativity is understanding tensor algebra and differential geometry. This is the basic cornerstone without which nothing will really take place in a proper manner. So before, as you can see this diagram, this is something you all understand. This is the vector which has got a tail and a head. So before Einstein, physics used ordinary numbers and vectors, but vectors were not enough to describe things like this, which is called the curvature of space-time. So space itself can bend and twist. How can vectors actually denote that? So tensors actually came in, and tensor are much more powerful, as we know today, in terms of machine learning and others. It is a mathematical tool that can describe how quantities that they can stay consistent no matter how much stretching and stretching and bending of the space that you do. So Einstein field equation itself are basically based on tensors. As you can see, this is what is called the Ricci curvature tensor. Then we got the metric tensor. Then we got stress energy momentum tensor. tensors. So without tensors, how can we understand Einstein field equation or the entire concept of general relativity? However, you can find very detailed video on Einstein field equation on this channel. So all these curvatures and the shapes that you can see at the bottom of the screen, these are basically expressed in the language of differential geometry and calculus. So obviously, as you can see, tensors are required, and differential geometry and tensor calculus is the basic language. So the authors actually put together the part 1, as you can see, very well arranged and very scientifically done. It is called Elements of Differential Geometry. So this is the alphabet of GR, without which nothing will happen. So first step, understanding elements of differential geometry, and the table of contents actually shows that. Now, the second concept which the author takes forward are called differentiable manifolds. Before I go ahead and explain you the table of contents, first I need to justify you why we are taking from tensors to manifolds. Now, suppose I take a kind of a sphere and you are standing here and you start moving. So all these red arrows and dots are actually showing that you are moving from this place to this place. Now you have moved. I understand that it looks from the top. If somebody is watching this sphere, somebody is moving from here to here. Now if I take a kind of a surface like this is a kind of a local surface, and here also you start moving in the same manner. So what happens is that this becomes something which is called locally flat. That means that manifold or that surface which looks locally Euclidean, I mean to say locally flat, is basically called the concept of a manifold. So all of the physics which is taking place on the sphere is actually taking place, the same physics is taking place on a flat manifold. So that is why this is called a global space and this is called a local space. Now you might say, why? Because in local space we can use calculus, and that is why we are using the concept of manifold. Technically we say a surface is smooth if it is locally homeomorphic to an Euclidean plane. Simple. As you can see from global, I can see something which is happening local. So if I take those kind of a surface which has got a positive, negative and zero curvature, and if I take all those white boxes, then I can definitely say that these look locally flat. That means R of n can start from x1 to xn. That means it is homeomorphic to a Euclidean space. So not only that, if f is continuous and it continuous, then its inverse should always be continuous. And this is beautifully explained by the analogy of the coffee cup and the donut. The coffee cup turning to a donut and the donut turning to a coffee cup shows that a function and its inverse is also continuous. So we justify the point that differential manifold is basically applying calculus on these curved surfaces, without which how do we understand which one is curved, which one is flat, and the mathematics behind it. So differentiable manifold is something which we introduce in the second part of the learning. And as you know that in general relativity, space-time itself is a four-dimensional manifold. So we need those things in order to understand how things bend. Otherwise, how do we understand our gravity? So it starts very nice with the introduction to differentiable manifold, the history and how it evolves, and then it takes you to differentiable manifold. The third step which the authors take forward, and which is very again logical, is what is called tensor calculus. Now why tensor calculus? For example, when we are, as you now see that here all these surfaces, let me go back, are all basically curved in different ways. So from here what we can say in tensor calculus, we are actually not behaving with straight or plane surfaces. Here we study how geometry behaves under deformations. That means rotation is happening, translation is happening, and that there are a lot of changes in coordinates. So here you can see the coordinate rotation, coordinate is being stretched into kind of an oblate, spheroid, ellipsoid, etc. So let us understand that the key idea is that physics should look the same no matter how you stretch, rotate, or you do anything with the coordinates. So that is the reason we find something which is this one, transformation groups. So exterior differentiation and integration, they give us the mathematical tools to describe quantities like flux, circulation and conservation in curved spaces. So general ideas from calculus to geometry. So as you know that symmetry and conservation laws are very central to physics, so all these ideas do connect. For example, Noether's theorem. So the mathematics here shows that how geometry and physical invariants or invariant quantities are related. So if you're stretching and you're squeezing or rotating, etc., the physics should remain the same, and in order to do that, what we need is what is called tensor calculus. Now, from tensor calculus, what we can also say that if we can apply, for example, the general rule of calculus, then they apply on the manifold. So as you can see here, it was originally, this idea was proposed by Ricci Curbastro and the student Tullio Levi-Civita, and this is what is called absolute differential calculus, our next step. It is just in modern days it is called tensor calculus. It was originally coined as absolute differential calculus. The reason it is absolute is because in ordinary calculus, when you take derivatives, your result depends on coordinate system, but here it is not. So Ricci and Levi-Civita developed a calculus which works on this kind of a curved surface, and it remains invariant under any kind of a transformation. So in order to do that, what we need are certain mathematical tools. For example, covariant derivative. It measures how a vector changes as it moves along a curved surface. We need something called Christoffel symbols. These are actually adjust the derivative to account for curvature. And then we need something which is called the Riemann curvature tensor. Quantities that how much space is curved measures the failure of vectors to return in their original directions, which you can think something of a parallel transport. So all this actually result in what we call the fourth step, that is from manifolds to tensor calculus. So absolute differential calculus, covariant derivatives, these things are being done. So till now what we have learned first is what we called is the tensor algebra, then we got a differentiable manifold and the tensor calculus. These are the four parts we have done. Now after this, the author actually takes a revisit of what is called classical physics. There is a reason for that. Let me show you. In general, you know that the basic Newton's second law of or something of force is being now replaced by geodesic equation, and the laws of gravity are now being replaced with Einstein field equation. So all this actually shows that relativity was not born out of imagination, but it was basically some kind of a problem on contradiction on Newton's mechanism and Maxwell's equation. So studying the limitations, which the authors have shown beautifully in this book, actually shows why and how Einstein replaced them. So the basic thing is that classical. So all of this under weak field approximation, geodesic equation will go back to F equals to ma, and Einstein field equation will go back to Newton's law of gravity. So that is why there is a quick revision in terms of Newtonian dynamics, Newtonian gravitation, and all of those things. So it's a good point that the authors, and I think you should also take a quick revisit on the Newtonian part of the classical physics. Obviously, from classical physics, the next part which comes is called special relativity. But hold on, the authors actually start special relativity on a very different note. It speaks of something of a concept which is called optical isotropy principle. In general, it means that light behaves in the same way in all directions. Now, the optical isotropy principle says that the speed and propagation of light are isotropic. They do not depend on the direction in which the light travels. So in terms of Newtonian mechanics, if we talk, then Newtonian physics, in Newtonian physics, light could have different velocities depending on the medium or direction, which led to theories like ether, etc., which I'm not going to talk about. But Einstein in 1905 actually told that the laws of the physics are the same in all inertial frames and the speed of light is constant. So what it actually led to is that when space-time is curved locally, light still behaves isotropically. So the optical isotropic principle actually holds, and what we get from here is that optical isotropy ensures that space-time has the Minkowski metric. This is one of the signatures of Minkowski metric. There is another minus, plus, plus, plus. All these I have explained in my course on general relativity. The basic idea that what we get from here is that optical isotropy, the uniformity of light's behavior in all directions. So in every local inertial frame, light travels at the same speed. So this is actually how the author starts. So in special relativity, as you can see here, the physical foundations are being given and the special relativity and Minkowski space, etc., which is a good point to start it. Now, once the authors or you have learned about special relativity, then comes a very important concept, which is called continuous systems and special relativity. And this is a very unique approach in building up your mathematical foundations. Now, what happens here is that special relativity actually begins with particles. That is, for example, a single point mass which is moving through space-time. But reality is not that easy. In reality, most physics, for example, fluid, gases, electromagnetic fields, even solids, are not made up of isolated points, but they are actually what we call continuous distributions of energy and momentum. So we need a relativistic description of continuous matter valid everywhere in space-time. So a continuous system is described not by trajectories, by fields. So continuous system introduces the concept of tensors or momentum tensor. So in relativistic physics, as you can see, everything is put together in one geometric object, which is the T mu nu, and this T mu nu will come later in Einstein field equation and it becomes the source term. So here you can see that this is something beautiful. It first tells about the limitation of using point-like particles. Then it goes in defining a system in terms of field or a continuous distribution. In order to measure that continuous distribution, we need momentum tensor, and that momentum tensor will again feature in Einstein's field equations. So this section, which you will see now, electrodynamics in moving media, actually uses these tensors, and it uses a momentum energy tensor, intrinsic deformation. So it is actually special relativity, but from point-like particles, it is moved in something which is called kind of a continuous system. So that is why continuous system and electrodynamics in moving media, which is now moving, actually describes everything. From here, once we are done with the Newtonian mechanics, the differentiable manifold tensors, etc., we now move in what is called a introduction to general relativity. Here, actually, the author basically talks about how Einstein took the great leap, and here you can see this nice animation showing that instead of force acting at a distance, Einstein told mass and energy curve, space-time, then stress energy momentum tensor and everything. So here, actually, the general relativity and cosmology is being introduced, and everything goes regarding the Palatin's variation principle, etc., all done in a very nice mathematical way. Now, here is something unique. This is a very good mathematical part which the authors take forward. It is called the Cauchy problems in Einstein field equation. Now, in physics, we generally called Cauchy problem as something that if I know the state of a physical system at one moment, can I predict that how this system will evolve? So in mathematical term, we can call it is the initial value problem for differential equation. This was actually theorized by Augustin Louis Cauchy, and it asks whether for a given sets of equation, can you find a unique and state solution for some special initial data. So if we take the Newton's law, for example, here, if I know, for example, x equal to 0 and the first derivative, then I can compute for any future. So this is the Cauchy problem. But the problem starts that in general theory of relativity, things become a little bit more complex. So it actually asks this: if we know the geometry and its rate and change of time on initial hypersurface, that is one slice of space-time, can we actually determine the future evolution of the entire system? So because here you can see that these equations are much more complicated. It is not as simple as Newton's ODEs. So if we know the shape of space and how it is bending right now, can we predict how space-time will evolve? So that was basically called the Cauchy problem for Einstein field equation. Things are not easy because it is not just an ordinary differential equations. So here, as you can see, the author, Romano and Fernari, when they say first considerations, they mean actually number one, can we specify what is called initial data continuously? Because you remember Einstein equations are constrained. Not every initial choice of geometry and every distribution will lead to a space-time. Second is that are the equations hyperbolic? That means in partial differential equation, for a system to have a good Cauchy problem, it must well possessed so that there is a solution, it is unique, and it depends on smoothness of the initial data. What is the initial nature of the initial, and further questions as it come forwards. So here you can see that this is the Cauchy problem which has been dealt beautifully in this book, and I think that you should also learn Cauchy problem for Einstein field equation. Now here is a quick hint that I wanted to give you. This Cauchy problem for Einstein field equation is being solved by a woman, and he died at the age of 102 years. Who is the person who actually solved this Cauchy problem for Einstein field equation? A woman, I can give you a hint. She died at 102 years. French woman. If you know her name and what was her contribution, please do let me know in the comment box. As we deal with the Cauchy problem, the next thing comes is the Schwarzschild black holes and cosmology. So here, as we all know, that this was the first initial solution possessed by Carl Schwarzschild, and this is the equation. What it tells is that it comes from the Einstein field equation. So if we take a non-rotating spherically symmetric and which has got no charge, a kind of a mass, then what we can say is that if this mass is compressed into a sphere, smaller than the Schwarzschild radius, then nothing can escape and it can form a black hole. So you, me, the table, the chair, the gas cylinder, etc., everything can be turned in a black hole. So the Schwarzschild metric is basically, you can think of a instruction manual for how space and time will behave around a heavy spherical body. And here you can see the table of contents comprises of the Schwarzschild solutions and black holes. This is where the table of contents and the video, I mean to say the entire content of the book is concluding. That means we have already gone through the step-by-step logical understanding of this book. Now here is a quick review overall which I think of this book. Now as you saw that the book is not only the table of contents, but I told you the way you should learn general relativity. So overall, I would say it is mathematically obviously very rigorous, and it lays down a strong emphasis on the foundation. So it starts with the elements of differential geometry, without which nothing is going to happen. Then it revises Newtonian dynamics, talks about special relativity, and then goes into general relativity and cosmology. So if you see, I have not given you a screenshot. In the preface, it actually told that nowadays writing a general relativity book is like finding up a grain of sand in the sea beach. So the authors actually try to map the mathematical objects to physical measurable quantities. That is why it is called a critical analysis. Apart from that, I would say the major strengths of the book is that it is very rigorous. It gives you mathematical preparation in terms of tensor algebra and everything. It is a balanced approach between classical and relativistic physics, because it do give a kind of a revision, etc. And it is good for advanced reader and graduate courses. So for those who want more than a cookbook presentation of relativity, I mean to say really serious, this would be an amazing book for you. The weaknesses and limitations, not much, but yes, definitely, as I told you, it is heavily mathematical. So you need to have a good understanding of differential geometry, manifolds, etc. It is not meant for casual learners. That means it is overall not for somebody who will relax on a sofa and will read this book. It is not meant for that. So I think it can be considered as a limitation, but for me, I think this should not be counted, because the book title itself tells it is a mathematical exposition. So in my opinion, if I talk about this book, then I would talk on these points. If you're really committed to understand relativity in terms of mathematics, you can read this book. Be prepared for mathematical effort because may want something more introductory first, which you can go ahead. The value, it is critical and it will give you a very good understanding of the mathematics. And this book actually invites the reader to think about relativity, not just you're applying. So I would say physically meaning attaches to coordinates, what assumptions underline the mathematical model, and how do we interpret in measurement terms. So definitely this is making you to think, and that is why it is called critical. Critical doesn't always mean that it is wrong or criticizing, but something which is making you think. And that is why we got the book called The Critic of Pure Reason by Immanuel Kant. I don't know if you have read philosophy or not. So that's all for today's video, the first video. Thank you very much for watching. If you have liked, please do subscribe to my channel Physics for Students and keep the bell icon ringing so that you get all the notification from Physics for Students. You can follow me on my other social media handles where I am very active, and you can write to me for any further clarifications, or you want to contact me via this email ID. So we are done with the first series of videos on the mathematical foundations of general relativity. 2 more videos are coming, so stay tuned, and few more videos we will continue serving you in terms of physics and mathematics by producing quality content on physics and mathematics. I will see you soon in the next video, but till then, may the good Lord be with you.